So geometric distribution has one other very important property that we're going to cover, and in particular, we're going to cover what we call the gambler's fallacy. Okay, so if the gambler loses 5 times in a row, will he be more likely to win? Okay, in the 6th round. Okay, so mathematically, we're just asking, well, if we know that, if it's a geometric distribution, right? If we know that he already loses the first 5 times, so the conditional probability, right? Like it's going to be already loses for 5 times. What's the chance that he will be winning? Okay, for the next one. So essentially, we're asking, well, whether this conditional distribution going over there or the extra information that we know about the gambler loses 5 times in a row, would that affect whether he's going to win in the 6th or not? Okay, so intuitively, I guess you will probably say that, well, no, because each game is independent from each other, right? So it doesn't really matter how many games he loses already, the next round is always a new round. Okay, but which is true. And then in our formal term, we actually can define what we call like distribution is memoryless. Okay, memoryless meaning that whatever happened before doesn't really affect what happened, what's going to happen next, right? So mathematically, okay, we have in this case, right? So the random variable x, okay, conditioning on the fact that random variable x is larger than m, the chance that the random variable going to be larger than n minus k, okay, so k more games, you can think of it in that way, is the same as if we don't know about this n before. Okay, so it's the same as the marginal probability of x is greater than k. Okay, so we call this memoryless. Okay, and in fact, geometric random variable geometric distribution is memoryless. Okay, so we're gonna use this definition to show you why that is the case. Okay. All right, so if I want to focus on, right, this conditional probability, okay, we know that conditional probability will be whatever you have in the condition was going to be in the denominator, right? And then the intersection of the condition and the non-condition thing should be in the numerator. And in this case, the intersection will just be x is greater than n minus k. Okay, so both of this, as you can see, especially from the previous video about the CDF, okay, CDF of the geometric distribution, we know that, well, if x is greater than, we need to know the probability of x is greater than n minus k. That is the same as saying that all of the n minus k trials all of them have to be fail. Okay, so it's 1 minus p, failure probability to the power n plus k, divided by the failure probability 1 minus p, sorry, to the power of n. And then if we canceled out the n, right, it's going to be 1 minus p to the power of k, which is actually also just the probability of x greater than k. Okay, so this is what we mean by, well, through the gambler's fallacy, we introduce the definition of memoryless, okay, and we show that geometric distribution is memoryless. And through the gambler's fallacy, we talked about it already that, well, intuitively, each game is independent, right? So, well, if you already loses 5 times, it doesn't mean that it will be more likely or less likely, right, to win or lose in the 6th round. Okay, they're independent. Okay, and mathematically, that's what we mean by memoryless. And then we also show it mathematically that the geometric distribution is memoryless. Okay, so this is a very important property of geometric distribution. Okay, so please keep that in mind, and then this might be pretty handy in solving certain exercises. So lastly, I'm going to show you some of the PMF. Okay, PMF for geometric distribution. So remember, there's only one parameter p, right? The success probability. Okay, so all of them are again unimodal, right? You only have one maximum value, and the tail of it, okay, is getting actually shorter, right? As we increase p. So just to refresh your memory, that the expectation of the geometric distribution is 1 over p, okay, and the variance of the geometric distribution is 1 minus p over p squared. Okay, so overall, if we plug in those 3 different values, I'm sure we're going to see why the tail is getting shorter. Okay, because the variance, I guess, as p increases. Okay, as p increases, the variance decreases. Okay, and the mean as well right? As P increases, mean is decreasing. Okay, that's why we're seeing a longer tail as P increases, as well as mean is more concentrated to smaller values of X. Okay, and actually intuitively also makes sense if you think about it, because P is the success probability, right? And then X, we're showing you X is the number of games or number of trials that you have to do until a success happens, right? So if P is really small, meaning that it's really unlikely to succeed, then you will just need more trials, right? So that's why when P equals to 0.2, in this case, you have a longer tail, and then the mean is also going to be a little bit larger, okay? But if you have like the last one over here, that is very likely for you to succeed on each round, okay? 0.8, 80%, okay? So most likely, well, you only need to play 1 or 2 rounds and then the game is going to end, right? And then that's why we are seeing a small expectation as well as a shorter tail, meaning that it's a smaller variance.